Okay, so then welcome everyone to another DeepThought summer student talk. I see people are still joining. So today we have a talk given by Ishaan, Arjit, and Shrijan on their summer project on the fine-tuned universe, and they're giving an overview on fine-tuning questions. And with that, I hand over to Ishaan, who's starting.
Yeah, so is my voice audible?
Yeah, Ishaan,
Hello.
you're audible. Yeah.
Okay, fine, great. So, hello everyone, welcome. Thanks for coming. Today, I, along with my group, will present our summer project, which we did as a part of the DeepThought Alpha project under Professor Lucas Raumreiser. We worked on fine-tuned universes, which was based on the paper by Fred Adams. It actually was a review paper. It was titled The Degree of Fine-Tuning in Our Universe and Others. So today we'll present an overview of the same. The next slide, please. The outline of the talk is as follows. I will cover the first three parts. Then Shrijan will take over for particle physics, and then Arjit will continue with star formation, planets, and conclusion. And finally, Shrijan will give a brief description of the code we have used for plotting the constraints. So yeah, next. So yeah, purposely I've used this template because Fred Adams has given an analogy in his paper that fine-tuning is like rotating the knob of a radio. So as you can see, the left knob is towards the cooler side, which kind of depicts that the universe has cooled down since the beginning. And so yeah, let me start by giving a brief introduction. In a simple terms, fine-tuning is a process in which a certain number of parameters are adjusted precisely to fit certain observation. We say that our universe is fine-tuned for the existence of complex life. We have just extended the concept to multiverse. We have varied certain astrophysical parameters with the help of certain constraints to check for habitable universes with different characteristics than our own. Further, we can broadly categorize fine-tuning in two types, sensitive and hierarchical, which I'll discuss in detail in the next section. So yeah, the problem formulation. The method we have used is firstly we have identified the parameters which can be varied and then further determined the allowed range of these parameters for development of complexity and henceforth the observers. So next. Yeah, I'll start with the cosmological constant problem. And yeah, next please. So yeah, we can define our universe by few cosmological parameters, one of which is dark energy. This acts as a cosmological constant and is one of the dominant components of our cosmos, as it contributes to around 68% of total energy in our present day observable universe. There is a couple problem due to the existence of non-zero energy density, which arises from the general theory of relativity. It allows for a non-zero vacuum energy density. Nonetheless, it poses two coupled problems: the cosmological constant problem, and then using that we put bounds on cosmological constant because there is no theory which predicts exactly what is the value of cosmological constant. Next. So related to hierarchical fine-tuning problem, which argues that if vacuum energy density plays a significant role at present time, its value must be extremely small relative to the theoretically expected values. But that's not the case. The next problem puts some bounds on the range of values of cosmological constant. The argument is that if the vacuum density is large enough, it will affect the structure formation. It will try to suppress. In an arbitrary universe with large cosmological constant, the structure formation will not be able to detach the structure will not be able to attach itself from the background expanding universe because the expansion rate will be far greater. So we can explain the cosmological constant problem from two different approaches. The first one is the classical one. The second is the quantum one. So let me start with the classical one. We start with the Einstein field equations with the cosmological constant, obviously, to accommodate an accelerating universe. Further, through dimensional analysis, gives us an energy density in terms of gravitational constant, which puts the value of the vacuum energy density around 10 to minus 10, which is to 10 to minus to 10 to the power 112, which is not as observed in our universe. Next, also through the quantum field theory approach, if we in general, the vacuum has a non-zero energy density. It's analogous to 0 point energy of any quantum system. We take the expectation value of the energy momentum tensor, which is directly proportional to the metric of that universe in which it is defined. So after working out the mathematics, we get the same results. So for a completeness sake, we could say that the vacuum energy density can arise on both sides of the Einstein field equation. And despite many ideas, we don't have a correct theory which predicts it. So yeah, it can originate on the left side as well as on the right hand side. Current experiments indicate that the cosmological constant or the vacuum energy density is not equal to zero, but it doesn't distinguish between the pure cosmological constant or the expectation value of the energy momentum tensor. So yeah, next. Although the vacuum energy density is not predictable by any theory, its value is in our universe is nonetheless constrained by cosmological considerations. So we put two constraints on this. First one is a weak bound which arises from the argument that the universe must have a matter-dominated era. Therefore, the energy density of the vacuum must be smaller than the energy density of the universe at the epoch of equality, which gives the following relation. The constraint relation given here is stated in terms of lambda. So, it's related to the vacuum energy density by the expression given below. So, we can just take the power of 4 to take in terms of the rho lambda. Next. Yeah, a strong bound arises from the requirement that the galaxy formation occurs before the expansion of the universe starts to accelerate due to vacuum energy. It's kind of obvious. The constraints originating from this argument require that the quasars form by redshift of 4.5, which gives the following relation, where rho equality is the energy density at the correct moment, and the Q is the primordial density fluctuation. So including both the relation, we get the final relation which is given in the bottom, and we have plotted that constraint in log format, which we have scaled down to with the help of the values of rho lambda in our universe and Q in our universe. So yeah, you can go to the next slide. So yeah, this is a plot we get. The red line denotes our universe, and the different plots we are getting is due to the different values of eta. Eta is the baryon to photon ratio, which is for the different plots we have. Like for the red one, we have of our universe, which is 6 into 10 to minus 10, and then 10 to minus 9, and so on till 10 to minus 6 from bottom to top. And the shaded regions are the forbidden regions because of the large and small values of Q, the primordial density fluctuation. Large values of Q are ruled out because it would overproduce black holes, the right hand side of the figure, and the left hand side for the smaller values of Q, because if for smaller values of Q, the gas or the galaxies would be too rarefied to cool and condense into stars. So that's uh, was for the cosmological constant problem. Now I move on to the galaxy formation. Yeah, next slide. Here we have again adopted the same method that first we clarify the parameters to be varied, which are dark matter and baryons, and then we study its variation. So the parameters are the dark matter parameter delta and the barion to photon ratio eta. So here also we have a couple of constraints. The first constraint is uh, due to the argument that if the mass content is too large, then the epoch of matter domination would occur before the Big Bang nucleosynthesis, which is kind of observed. Roughly, the energy scale of Big Bang nucleosynthesis can be comparable to the electron mass. So we get the following constraint, which is uh, simple. I mean, the sum of the baryons and the dark matter, and we have assumed here that the dark matter has the same mass as that of baryons, the dark matter particles, whatever they are. So we have multiplied it by the mass of proton, and then we have equated with the uh, mass of electron. So we get the following relation. Secondly, we have the requirement for structures to become non-linear. For somewhat smaller, if we have a smaller matter abundance, large-scale structures can detach from the expanding universe and become non-linear before epoch of decoupling. So here we have the background is that the temperature of the uh, non-linearity, non-linear structures is equal to the temperature at recombination, which comes from which is derived from the Saha ionization equation. So put it all together, we get the following constraints. Next. So yeah, the third one is that in our universe, the epoch of recombination and photon decoupling occur after the matter radiation equality. So what would happen if we reverse that? Nothing much will happen, but still the boundary where this happen has the form of the following equation, the first one. The fourth one comes from the fact that if there are less matter abundances, then this fragmentation will occur. In the sense that if we take the eta below delta, so the delta by eta is greater than 300, which means that the dark matter is in more abundance than the baryons. So this fragmentation would occur, and that which is not suitable for a habitable universe. So the final equation comes from the silk damping. Silk damping is generally a dissipation of small scale perturbation which are caused by photons random walking out from the overdense region. It's kind of like a diffusion of photons from a highly dense region to a lower dense region. So the fluctuations which cause galaxies to form like our own Milky Way galaxy, those fluctuations smooths out. If the condition for that is if we have a unity baryon density. So in unity means that both of them are almost equal. So we get this relation. Combining all of that again, and we get the final plot, which is in the next slide, please. So yeah, the shaded region denotes that the first constraint relation, which was the matter dominated before Big Bang nucleosynthesis. The region between the purple and the green curve represents the non-linearity before decoupling, and the region beneath the pink curve represents the equality after decoupling, and the region above the red curve represents the disk fragmentation, and below is the silk damping, and the dot you all could see is the our current universe in which we are living. So yeah, in the sense that the habitable area is only between the red, the sand, the pink, and the blue area. So yeah, next. So now I'll give over to Shrijan, who will discuss further about particle physics.
Yeah, thank you, Ishaan, for discussing on cosmological constant and galaxy formation. So after discussing cosmology and stuff like that, we wonder what argument of fine-tuning we could model around particle physics. Particle physicists would obviously argue, the first thing he would argue is, let's use standard model of particle physics, because we have these 26 fundamental constants, these quarks, leptons, bosons, Higgs bosons, many angles. So they would argue, one would argue that let's just use say 26 parameters and we'll have a large existence space, because we'll have many constraints regarding that. But is that true? No, because it's our limitation that there is no higher level description yet of all the fundamental parameters, of all the 26 fundamental parameters. Only a few give a meaningful higher level description of fine-tuning as of now. So like the workable parameters here will be the mass of up quark, mass of down quark, the strong coupling constant which relates to the strong force, then fine structure constant which obviously relates to electromagnetic force, because alpha is E square by hc in natural units, and beta is of course shall be there, which is the electron to proton mass ratio, and some other miscellaneous workable parameters are also there, like the difference of mass between a neutron and a proton, and many other some miscellaneous, but they are derived from these parameters itself. So let's go about the first section of particle physics. We go about nuclear stability. So when we talk about nuclear stability, we first argue in terms of quarks, and then go to protons and neutrons. But the workable parameters shall be quarks only, because in nuclear stability, basically, when we argue where we model some fine-tuning argument on nuclear stability, usually that is some nuclear reaction that is we are modeling. So for a modeling a nuclear reaction towards a fine-tuning argument, that is the generally preferable way is that we don't want a nuclear reaction to proceed in the generalized way. For example, protons comprise of 2 up quarks and 1 down quark, and neutrons of 1 up quark and 2 down quark. And we know that beta decay in the lower level description where of up quarks and down quarks is that up quark goes to down quark plus a positron plus a neutrino, and down quark goes to up quark plus an electron plus an antineutrino, where we neglect neutrino and antineutrino for their smallest of their mass. It's pretty small. So example I'm putting here is that we don't want a proton, which is a UUD state, to convert into a symmetric UUU state. The universe that shall, I mean, the argument is that it's not that the universe that shall have protons with UUU state won't be habitable. The thing is, those universes will be much different than our universe. So that is the argument I'll use many times, and maybe Arjit sir shall also use in stellar formation that. So we don't want a UUD to convert into a UUU state. So we don't want this to happen. D goes to U plus electron plus antineutrino. So basically, we don't want this reaction to proceed in the generalized direction. So the constraint that comes out of this whole analysis is this, that MD is less than MU plus ME plus E3, where ME is the mass of electron, MU is the mass of up quark, MD is the mass of down quark, and E3 is the energy required to produce an antisymmetric state of 3 quarks, so that is from UUU to UUD state. So basically, if the mass on this side is less, the nuclear reaction won't proceed. obviously that's the whole principle of nuclear reactions. So that is the kind of modeling we do in particle nuclear stability. So the other constraint is also that we don't want a neutron, which is a UDD state, to convert into a DDD state. So this is that constraint that arrives from that. Yeah, I'll take up some more examples. Like we want the stability of free protons and hydrogen. Like by free protons, I mean we don't want a neutron to proton to convert it to a neutron plus a positron plus a neutrino. So basically this equation comes into picture, that mu plus delta em plus is less than md plus me. Where this delta em factor comes due to the fact that we are now considering the interaction between proton and neutron, and when we consider interaction within proton and neutron and not inside them, there's this additional delta em factor, which is the electromagnetic mass difference between proton and neutron, which comes due to QCD analysis through quantum chromodynamics. It comes QCD and QED both. So yeah, this delta M comes from that. So this constraint is what we get from this. We curbing this nuclear reaction. If we want to curb hydrogen to not convert into a neutron plus a neutrino. So basically, the hydrogen absorbs an electron and converts into a neutron. So essentially, we get this, that mu plus delta M plus me goes to this side is less than md. So basically, these are some of the examples. And yeah, it may not be visible yet, but me is actually the beta we were talking about earlier, the electron to proton mass ratio. So the electron to proton mass ratio also creeps into nuclear stability in a way. So yeah, those were some examples, and due to time constraint, of course, we couldn't discuss every other constraint. So these were all many other consideration, like stability of diprotons and stability of pions and stuff like that. So this is the existence space we get. The shaded region is the existence space we get. And yeah, and the axis, I'll explain the axis, that on y-axis we have md by md0, and on x-axis we have mu by mu0. Well, where md0 and mu0 represent the mass of down quark and up quark in our universe, and md and mu is the workable existence space in some other universe. So this is the existence space we get through that, and this small dot on the boundary, we are lucky enough to be in the shaded region. This small dot on the boundary is actually our universe. This is our universe. So yeah, this is the nuclear stability section. So let's now move from nuclear to an atomic level. So when we move from a nuclear to an atomic level, we'll have all sorts of things like electron orbit, the interaction between electron and proton, and relativity of electrons, and many other things. I'll discuss them. So basically, let's just first consider the total energy of an electron, which is simply like if we consider the potential energy minus E square by R and kinetic energy as P square by 2m. By some simple substitution using de Broglie's method, de Broglie's hypothesis, one may write E equal to this total energy as this, and differentiating it, of course, we get the radius of the first electronic orbit, and it comes out to be 8.3 into 10 to the power minus 15 alpha beta inverse. So basically, we know that, so I'll tell you that the nucleus radius is usually around 10 to the power minus 15 and minus 16, and the electron radius is around 10 to the power minus 10 or 10 to the power minus 11, the first electronic radius. So if we want the chemistry in of any universe to function like ours, we would essentially want this value to be around 10 to the power minus 10 or 10 to the power minus 11. So for that, we would require alpha beta to be less than 1. So that is where one of these constraints come in, that alpha should be less than 1 and beta should be less than 1. So I'll first discuss alpha less than 1. So one of the implications of alpha less than 1 is actually electrons remain non-relativistic. Actually, electrons are low relativistic, but they aren't ultra relativistic. But if alpha is if alpha is nearly 1 or somewhat greater than that, they will become ultra relativistic, and that will cause some problems of the spinning around the nucleus. And this less than is actually very important, because if we put just a less than sign of less than 1, it will actually come about to be equal to the strong coupling constant, and we don't necessarily want that, and I'll discuss that later why we don't necessarily want that. And another one of the conclusions that follow from this constraint is that planets remain smaller than stars. Arjit shall discuss this later, that alpha less than 1 is also implies that planets also remain smaller than stars. So that is one of those conclusions. And then we have, so we got beta less than 1, but there's another method to get beta less than 1 constraint. So that is, we consider the fluctuation of the relative fluctuation of the ion in the lattice core. So the relative fluctuation of the ion through uncertainty principle and somewhat of statistical physics, if we use, is this value, which is mean square position divided by the uncertainty of the electron. So if we take the root, it comes out to be beta to the power 1/4, and we necessarily want that fluctuation to be less than 1. So this is one of the ways we get this beta less than 1 constraint. And it's just not beta less than 1, it's beta to the power 1/4 less than 1. So some of the implications of this is, as this is derived from the fact that relative fluctuation of ion in the lattice is should be less than 1, the nuclei in the lattice is actually accurately and rigidly located in a solid. It doesn't fluctuate a lot. And if it fluctuates a lot, it will cause problems in DNA replication fidelity. For those who don't know, our DNA, the human DNA, actually me, you, everyone, share 99.9% common DNA. So if this constraint is not fulfilled, fluctuations will happen, and DNA replication fidelity, the way DNA replicates itself, won't happen so efficiently. So we won't be humans anyways after if this constraint doesn't hold, because the DNA won't replicate to that high value of 99.9%. So that's that. And there's also a flipping thing, like we may flip this constraint, and why? Some literature actually suggests that it is not necessary for the electron to orbit around the nucleus and the proton to be inside the nucleus. It is possible that in some universes, electron is inside the nucleus and proton is actually revolving around the nucleus. So obviously, in that case, the beta will be flipped. Like if beta is ME by MP, it will be MP by ME. So basically, we had beta less than 1, and it shall transform to beta greater than 1. And we chose 1 less than 1 as 1/3. So beta greater than 81 we get. So yeah, using some more equations, some more constraints, we obtain this parameter space that you may see that this dot here is our universe, and actually this small 2 lines are actually the GUT consideration, grand unified theory consideration, if we take into picture. And yeah, the axis shows log beta by beta 0 and log alpha by alpha 0, where beta 0 and alpha 0 are the values of beta and alpha in our universe, and beta and alpha are obviously values of electron to proton mass ratio and fine structure constant in some other universe. So yeah, this is the existence space we get from here. So yeah, so let's again go back to nucleus, and when we go back to nucleus again, we shall consider strong force. So we know that strong force is majorly described at a much more deeper level by quantum chromodynamics. But does it help in formulating some fine-tuning argument? No, because it is so deep that it doesn't provide a high-level description at the nucleus and its working, some fine-tuning argument related to that. So we use the help of fission. So basically, so what is alpha S? Alpha S basically represents strong force attraction, and strong force attraction actually binds the nucleons together, all the protons and neutrons together. Otherwise, we know that protons repel each other, and they would like break apart if put together, but the strong force actually holds them together. So fission actually happens at a much more higher atomic number, because the electromagnetic repulsion there is so high that the strong force cannot accommodate that attraction anymore. But we don't want a fission to happen at maybe like carbon or hydrogen or lithium, just like that at room temperature or something like that. We don't want that to happen. So for that, we consider this constraint that the alpha is by alpha 0, which is the strength of strong force, should be greater than this this value of alpha by alpha 0, which is the electromagnetic strength, so that the nucleus stays together in small atomic number. But as we know, we cannot completely neglect the possibility of nuclear processes, because they are also important for stellar formation, for galaxy formation, for everything. Nuclear processes are important, so we cannot neglect that. So we essentially at higher nucleus and lower nucleus also, we would want that. So here we use binding energy. So we want that if we provide an atom, a proton with some binding energy, it should come out of the nucleus and perform some nuclear processes. So Fe56 has the highest binding energy per nucleon, which we call E56. So we compare that if we give an energy to a proton, which is E56, and this value shall be the lowest for E56 only, because E56 is the highest among all the nucleons, among all the atoms. So this should be greater than the strength of strength of strong force for that proton to break apart. So yeah, that sort of gives us the freedom that nuclear processes can also happen. Also, there are these miscellaneous constraints, like the electron orbit should be greater than the nuclear radius, because we want the universe we are considering to function like ours. So this constraint comes into picture. And if we consider, and yeah, that's a fact that we want the chemical energy to be less than nuclear energy, because when we mix two chemicals together, we don't want their nuclear configuration to change every time we mix them. We want the chemical configuration, the electrons to react, and not the nucleons to break apart every time they react. So essentially, we would want that nuclear energy is more than chemical energy, so that chemical reactions take place. So yeah, this constraint comes into picture, but these constraints are not too significant, because beta is already there, and the value of beta is already 10 to the power in order of magnitude of 10 to the power -3. So yeah, so including some more constraints, we make this plot, and you may see that the y-axis is log of alpha is by alpha is 0, and x-axis is log of alpha by alpha 0, where alpha is 0 and alpha 0 are the value of strong complex constant and fine structure constant in our universe, and alpha is and alpha is in some other universe. So we take the log to compare the order of magnitude they vary. So we see this shaded region we have is the viable existence space, and this small dot in the center is us here in this universe. So we may see that strong force actually doesn't allow much freedom as compared to nuclear stability section and the beta alpha plane. So this plane is fairly small, and yeah. So yeah, thank you. I would like to give the presentation now to Arjit to continue for stars and stellar formation. Yeah, thank you.
Thank you, Shrijan. So hello everyone, and I'll be discussing about stars and stellar formation. So we already know that stars are very essential for habitability of our universe, and we presume it does makes equally importance for other universe or multiverse, as we say. So we firstly define why stars are so important. We all know that stars are very essential for planet formation and for life to grow on planet, and they provide sufficient energy for the planet, and they also produce heavy nuclei, which ultimately forms the complex structures like planets and biological entities altogether. So start with we start with the mass constraint of the star. So we discuss how big can star be and how small. We define the limits of the stars, the mass of it, basically. So we first define that argue that the stellar mass should be less than the galactic mass scale. So for that, the galactic mass is, as seen in this constraint, is approximately equals the alpha g times minus half and alpha to the power 5, which is approximately equals to beta to the power minus half and m star. M star is the average stellar mass. And this is the constraint responsible for the star to have less mass than its host galaxy. And second thing we jump on to is the requirement that what should be the minimum star mass. So we argue that some approximate limit as to how large or small the star's mass could be, and the minimum star mass is determined by the requirement that that they have sufficiently high central temperature in the face of degeneracy pressure, and the maximum stellar mass is determined by that, like the radiation pressure shouldn't exceed the the gravitational pressure of the gas pressure by a large margin. So, Shrijan, next, please. So here you can see the minimum and maximum stellar conditions are mentioned. So for a star to exist, it should be in between these two limits. So for a stellar proper stellar configuration, the maximum stellar mass should be greater than the minimum stellar mass, as we can say. So from equating those two constraints, we end up with beta, which is, it should always be greater than 10 to the power minus 8 by 3 alpha square. Yeah. So as we discussed this mass of star, now we discuss the configuration of the star. The stable stellar configuration should exist, and we define the range of parameter that allows the parameter space actually that allows it for the existence of stars. And for this, it is very useful to work with the semi-analytical model for stellar structure to define the basis of for providing constraint. And for that, we end up with this larger constraint. And as it's not possible to discuss all of it, I'll just explain all the terms in it, which make some sense. So Eg over there is the Gamow energy, and since we are considering hydrogen fusion in star only, so it this term turns out to be equals to pi square alpha square into mass of proton into c square. And c star over there is a nuclear reaction parameter, and this has a value of 2 into 10 to the power minus 3 approximately if for our universe. M star over there is obviously, as we used earlier, which is standard stellar mass, and which equals to alpha g to the power minus 3 by 2 into mass of proton. And average of M is the mean mass of the particle that makes up the star. So we usually take that to be a mass of proton, as it usually consists of proton only. And N over there is the polytropic index, and we take it to be 3 by 2. Kappa naught over there is the stellar opacity scale. And finally, L star and mu star are dimensionless integrals of order unity. On the left-hand side, we can see I theta c. I theta c is actually a scale for central temperature of the star, and we approximate that value to be 3 by E root over 3 pi theta c into e to the power minus 3 theta c. And this approximation is very correct within a factor of 2, we can say. Shrijan. So for stellar nuclear burning, we jump onto the topic stellar nuclear burning, and we argue that the star should live long enough so that it allows for the observers to occur. So for that, we have approximate time limit. We say that star should at least live for around 1 million years for life to occur. So for in quantum mechanical tunneling, as we know, is dependent upon the fine-tuning constant and the fine structure constant. So if alpha becomes too small, then it becomes too small, and then this also becomes too small, and consequently star burns all their fuel at an instant, and we don't want that. We want star to live long enough for the occurrence of life. And that gives out this constraint, which is alpha squared beta should always be greater than 2.62 into 10 to the power minus 12. So finally, we plot all the constraints discussed earlier in this graph, which is in beta alpha plane. This shows the habitability for stars. And over here, we can see the black curve from usually required fine structure constant has to be much less than 1. And the red one is that designate the galaxy should have greater mass than the stellar mass. And the cyan line over there shows that beta should always be less than 1. This black line and the cyan line already have been discussed by Shrijan in earlier particle physics stages. And the blue one restricts the stars to burn all of its fuel at once, and the green one requires the minimum stellar mass should be less than the maximum stellar mass. The black dot over here, as usual, is the position of our universal condition, and the shaded region gives out to the the habitable region for other universe to have their stars in there. Shrijan? So we now jump onto a very similar curve, but this also gives the a parameter space for the stars to exist. So and this has alpha G and alpha in the alpha G and alpha plane. The green curve over here is the shows that the galaxy should have a larger mass than the typical stellar mass, and the black curve is required that stable stellar configuration should exist, and the shaded region delineate the position of the plane that remains after enforcing the following constraint we already discussed, and the black dot in the center symbolizes our universes. This curve can further be constrained, and the space will decrease further upon imposing many other constraints. Shrijan? So those were the conditions for the stars to exist, and only some though. But we jump onto the planet condition for the planet for it to have a stable life form and to have a proper biosphere for it. As we all know that planets originate on stars, as in our universe they do, and we also take it for granted that they also do in the same way in other universes also. So the habitability of planet is very necessary, and for them to have a proper biosphere for functioning. So we here also start with the constraint of mass. The planetary mass has to be smaller than the stellar mass, which seems very obvious, but it is a very necessary condition. So mass of planet should always be equal to alpha to the power 3/2 into mass, typical mass of the stars. And thus here also we are constraining alpha to be very much less than 1. And also quite obviously another necessary but not sufficient condition from the fact that the planetary mass should be less than the galactic mass, and thus alpha g is less than alpha to the power 7 and beta inverse. So other consideration comes from the fact that the planet should also be large enough to have a living biosphere. So if F bio over there, that is a factor of mass of host planet is larger than the biosphere, which gives us the constraint that alpha by alpha g should always be greater than F bio into 12 into QB to the power 2 by 3 A square, which is approximately equal to 10 to the power 30 F bio to the power 2 by 3. And QB over here is the information constant content in our biosphere, and which is approximately be equal to 4 into 10 to the power 40 bits. Shrijan? Yeah. Another constraint comes from the fact that iron should be more abundant than nickel and chromium. And we ask the question, why is that so important? Iron basically is very important for emergence of complex life forms. And Earth's core has iron that possesses magnetic field that shields us from the cosmic rays, and iron is there in almost every organism and helps in DNA synthesis, oxygen transport, as it's present in hemoglobin in our body. Using to constrain this statement, using the binding energy from semi-empirical formula, semi-empirical mass formula, we arrive at the condition that alpha should always be greater than 1 by 205 and always be less than 195. Shrijan? A more stricter constraint comes from the fact if we consider the radiogenic heat of Earth. So the radiogenic heat, this is very important for life because this provides nearly half of the Earth's internal energy powering planet's tectonic plates and the process, and that continuously delivers the raw material necessary for life to for the Earth on the Earth's surface. And after imposing this constraint, we end up with the form that alpha should always be greater than 1 by 153 and should always be less than 1 by 136. So concluding the constraint imposes here are much basic and discussed yet, and a full description of them are yet not exhaustively complete, and we have not considered anything related to the planet formation and some fine-tuning regarding them. And we yet don't know how exactly the life actually formed, so we cannot comment much on that. So coming to the plots, we have plotted everything we discussed at the constraint related to planet. We have plotted on over here, and this is also in alpha G alpha plane. And the green curve over here shows that the mass of the planet should be less than the typical mass of the stars. And the magenta line shows that the planet's mass should be big enough for to support biosphere. The cyan line over here shows that the mass of galaxies to be much more than the that of planet. And the red line over there shows that the fact that iron should have more abundance than nickel and chromium. The black dot over there obviously again is represents our universe, and the shaded region is the viable existence for planets to occur in multiverse scenario. So now we conclude our presentation with the discussion that how we do fine tuning and why we do fine tuning. Shrijan? Yeah, the first step we always have, as you can see, always have followed that we always pick up a constraint and see whether its parameter space is viable enough for others and viable enough for what is the range of it, and whether the observers can occur and if we change the things very much or not. But as we went through all of it, we came across some general trends in this, and I'm going to discuss that now. So the allowed parameter space is enormous. So as we have seen that the most relevant parameters can vary several orders of magnitude and still allow development of complex structures from atoms to stars to galaxies, and still be able to function properly. This is as earlier thought, we are not exactly on the knife's edge, as we say. So the second argument is that the particle physics is more sensitive than astrophysics. So the particle physics considerations are more constraining than astrophysical constraints. Like the allowed mass range of light quark is smaller than the corresponding range of the astrophysical parameters, including fluctuation amplitude and the variant of photon ratio. It's the dark matter counterpart, and the energy density of the vacuum. And so on, we move on to the third point, the large hierarchy remains. So what I mean by that is that a universe in general exhibit more hierarchical fine-tuning than it does sensitive fine-tuning. Like gravity must be weak, as we all know. So even if the parameter of physics and cosmology can diverge from their values of our universe by orders of magnitude, diminishing ratios are still required. These regimes from the physical parameters ultimately leads to the enormous range of mass and size scale observed in the universe, and we see that our universe actually exhibit more hierarchical fine-tuning than it does sensitive fine-tuning. Moving on to next point, the multiple variations are essential. So more possibilities for working successful universe arises if more than one parameter is allowed to vary. There's more probability that we end up with the observer a successful universe, as we say. So our universe does not lie in the center of parameter space, as we came to know, and the range of viable parameters are often asymmetric and are seldom considered in only one direction. The fine structure constant, for example, cannot be too large without compromising nuclear structure, but large ratios of strong to electromagnetic forces can lead to a wider variety of stable nuclei, as we have seen in particle physics section. So coming on to the next point, the fine structure constant must be small. Although the value can vary over a broad spectrum, several independent lines of arguments have been include that the fine structure constant must remain less than unity always. And we already have seen it many times in the graphs. So there are many myths and unnecessary conditions, as we thought earlier, were necessary for the existence of life, but no, they are not as necessary as they were thought they were. So many considerations often enforced on possible universes are not as severe as some previous work suggest. So in in universes with stable diproton, as we say, where nuclear reaction proceeds through a strong force only, the stars operate with somewhat lower central temperature, but they do not catastrophically burn their nuclear fuel at once. So as possible constraint on the weak coupling constant arises from the requirement that core collapse supernovas have optically thick neutrinos, but type 1A supernova can provide a heavily element even if the massive stars collapse to form black holes. So these were some of the general trends. And finally, we ask the question, is our universe maximally habitable? So spoilers alert, that's not possible, but our universe is not maximally habitable. But as we have suggested in this slide, that what could be changed to in order to end up with a more habitable universe than ours. So we argue that a smaller vacuum energy, the cosmological constant, would vanish. In this case, the universe could never enter in a late phase of accelerated expansion, and the scenario would favor structure formation, as the matter-dominated era would never end, and that would be a great thing. So, so the second point, more significant primordial fluctuations. So the amplitude Q of the primordial density fluctuation could be more effective. So if some inflation occurs in the ultra early era, then the probability of the proceeding density fluctuation could have a given amplitude with a given amplitude could be increasing function of Q. So the larger value of Q are more natural by then. Moving on to the next point, if we have more baryons, the ratio of baryon to photon ratio could be larger. Some enhancement leads to earlier matter domination. So which allow for large-scale structure to grow more earlier in our universe. Similarly, if we had more stars, then a range of stellar mass in our universe spans to a factor of about 1,000, but could be more prominent in other universe with other variations of the fundamental constants. One very interesting thing we could have achieved a stable beryllium-8 isotope could exist. So if the strong force was slightly more substantially larger than our universe, beryllium-8 could be a stable isotope, and this will enable such a universe to produce carbon without a triple alpha process, and which would be a very good thing, because as far as I know, that triple alpha process is very important for carbon protection, and carbon ultimately is very essential for life. So we also argue that a weaker gravity could also work in favor of habitable universe. So if the strength of gravity is weaker than in our universe, then the cosmos could expand more slowly, so that life would have more time to emerge and evolve. In addition, the stars and planets could grow more larger, allowing the larger animals and life forms to occur. So these were some of the argument I posed, and by this I conclude. And moving
thank
on.
you.
Yeah. So Shrijan will now continue with the code description. Thank you.
Yeah, thank you, Arjit, for your part. So after all this discussion, many sections of stellar formation, particle physics, cosmological consideration, we asked the first question Ishaan asked earlier: where's the knob? Like, where's the knob we use to vary all the parameter space here? So that knob, for creating that knob, we made this code. If you may see these two figures side by side, this is one of those nuclear stability fine-tuning argument I showed earlier. So this is the normal plot with beta equal to beta 0, where beta 0 is the electroproton mass ratio of our universe. If we change that to 10⁻², we may see that the plots change quite a bit and significantly, and the existence space also shoots up, like it also increases quite a bit. So yeah, it's important to and why beta into 10⁻², we also saw in one of the nuclear stability consideration that beta can be greater by 2 tens of order of magnitude. So yeah, so this is one. So for creating that, we created a code. So for that, let's first see the index here. So the index is what I'll explain later, how that index is used. But the index is actually just a relisting of all the constraints that were already there for the convenience of applying or actually using the code for yourself. So like we considered if you may remember, we considered the consideration of Fox-ability, that the protons may not convert it to a symmetric and neutrons may also not convert into a symmetric state. So from that, these two constraints are labeled as one. This has two, and in that way there are like 35 to 40 constraints we have, and we have some sub constraints with that. So these are this is the index list. You may remember that for later. And so some preliminaries of the code, that we imported the libraries, and we used the standard values used in our universe, and then we actually made a function that actually sums up all the parameters that we shall be using later, like the alpha G, baryon to photon ratio, the nuclear burning rate used by Arjit earlier, the up mass, down mass, up quark mass, down quark mass. And we provided all the values of our universe to those parameters, and we'll change that later. We'll see how that we change that later. So yeah, so this is the code of one of the sections. There are many sections, like this is nuclear stability. We have beta alpha plane, we have stellar formation, we have galaxy formation, and each section has its own code. So I'll take up the example of a nuclear stability. So if we see the argument of this function, nuclear stability, that's star arg v, up mass, down mass, beta mass p. So this is quite obvious that we mention the values of up quark mass, down quark mass, the value of beta and mass of proton here. This star arg v actually represents the index we need to be plotted. Like it may be that you don't want every index to be plotted. You don't want this constraint. You don't believe that this constraint is viable for existence. So you may remove that from the analysis you use later. So yeah, this is the code. So yeah, this is the if index 1 is chosen, then this shall be plotted where this is the index 1 we saw here. So this is that. So this is the code. We may directly see the implementation here, and that's sort of easy to explain that way. So yeah, so if we in the nuclear stability, we have these 5 indices that are important, like 1, 2, 3, 4, 5. And if we see, then we've put in place of the star arg v 1, 2, 3, 4, 5. And here we may see that we put 1, 3, 4. So if we don't want the constraint number 2 and 5, and if one user of this code doesn't actually believe that constraint 2 and 5 are necessary for existence of life, he or she may remove that constraint from this whole consideration. And important thing is, so this may be explained. And then the important thing is, why set these to 0? The thing is, in the code, we made this change that if the user sets the value of these parameters to be used in the constraint plotting, if the user sets it to 0, it won't let the user take search the value of that value and like literally light that every time he or she may write the code. So he may just write 0, and the standard universe value of our universe shall be taken there. But what if the earlier we considered beta equal to beta 0 into 10 to the power 2? What about that? So for that, just like all other things as being same, we just put beta equal to the value we want, and the beta value of beta 0 into 10 to the power 2 shall be taken. So yeah, and we may see that this is the plot that we were getting there, and we may actually shade this region here and shade this region here accordingly. The user may plot that accordingly. So yeah, that's all about the code description, and thank you. Yeah, thank you.
Right, thank you very much, Ishaan, Shrijan, Arjit, for a very nice talk and on fine-tuning in our universe and others. So perhaps there are questions from the audience. Okay, so if there are no questions, perhaps I have a few. Well, actually, let's just start here at the code description. So these are the code that you can configure to produce these nice plots here.
Yeah.
Do you also have some option to simply produce these curves as an array or a list of constraints that one can use, maybe combine?
Yeah, actually we have that also with us, but we didn't actually produce that here because that was sort of too easy to analyze. So basically, I'll explain that too. So there is another kind of function in the code we made that this is simply the thing that we made. Like if the user doesn't want to plot these figures, but instead wants this constraint. So we have made a constraint that if the user puts just the up quark mass, beta, and the down mass, the value of this down mass shall be there in the output. So yeah, that's also one of the functions we had made, but we didn't present that here. That was too easy. Yeah.
Okay, thank you. Yeah. So I see Benjamin has some questions. Maybe you want to ask. We cannot hear you. You have to unmute yourself.
Oh yeah, I'm sorry. So thank you, Free, for that very impressive talk, big collaboration, and a very nice code of code. I mean, it looks like, like a great deal of work. I would have a question related to the particle physics part, since this was mentioned to be the more sensitive part of the fine-tuning. And I mean, I don't remember my quantum field theory too much there at this point, but I know that all the leptons come in generations and associated with the quarks too. And I was wondering, all the constraints that you mentioned, they only apply to the lowest mass generation of particles. I understand that matter is mainly made of, is essentially only made of these, and in all relevant processes, there's only these counting. But is there any relevant consideration associated to the more heavy quarks, leptons, etc.? Is there new avenues for life, maybe in building matter out of something heavier, for example?
Okay, yeah. So if I understood your question correctly, you're asking that if there is some fine-tuning argument related to leptons or stuff like that.
Yeah, like if you can, for example, not take the electron to be the relevant particle in some processes, but say the muon. Although I have to say, I don't have a strong particle physics background. I don't actually know if it's possible to remove generation, etc. Well,
yeah. So the thing is here that I mentioned in the slides that actually there is no higher level description of all the fundamental constants. Actually, the only fundamental constants that we may use here are the up quark and down quark and electron, in fact. But as of now, there is no higher level description of any of the leptons, even not neutrinos and Higgs boson. Some fine tuning regarding that. Like if you may consider the upper quark and down quark, they are also very subatomic in nature, but we may relate them to beta decays, and that is something that we may relate to a fine tuning argument, that we don't want a beta decay to happen in certain direction. But the thing is, for leptons, for bosons and stuff like that, we can't formulate an or model an argument for fine tuning in that aspect at a higher level of description. So maybe that's the reason we don't have that as it.
So related to this question though, right, you have on, what was it, slide 24, this constraint that beta is either larger than 81 or smaller than 81.
Yeah.
And of course, I mean, if you replace, let's say you take different leptons like muon or tauon, then of course you could have you would change these ratios. So to what Benjamin was asking, right? You could, in principle, build other atoms. But I guess in our universe, at least, we would have to. These leptons are not stable, so these would not be stable atoms. But perhaps in other universes, these instabilities could change, and maybe they will be much more longer lived, and perhaps you could start building different atoms from different leptons. So,
yeah, that would be possible. Yeah.
Of course, then these ratios here would also perhaps allow for different configurations.
Yeah. True.
Benjamin, you had another question, or still microphone?
Yeah, sorry. Again, sorry. Yeah. Usually doesn't happen to me. Well. The other question I was going to ask was more related to astrophysics, which I know is, or as you said, is less sensitive than particle physics. But in general, I was wondering, this might be completely a dream idea, really, but could you imagine realizing a universe in which you don't need the stars per se, in which you don't need this hierarchy of planets, stars, galaxies, but instead, if you say you have strong primordial fluctuations and strong, say, black hole formation, and you have planets that orbit a black hole, or like whatever your like galaxy equivalent thing is made of, such that the inner accretion processes, again, it's not exactly my subject, but whatever, say there is accretion processes that would heat up the environment of this inner central object so much that planets could potentially live in that. I mean, it's very exotic, I assume, but is that at some point also taken into considerations of the fine-tuning argument? Does it significantly extend the range of parameters too?
Yeah, I think it might be possible for it to happen, but you say living near a black hole, the span of life wouldn't be as large for the complex life to occur, I guess. So that might not be as stable. What do you say? A civilization would not be possible, I guess. But yeah, you can say that simple structure could occur in that scenario also. But stars are very essential, as they also provide us with the heavier nuclei essential for life and carbon and all, which are very important. But as I earlier said, that and that heavier metals and all can also be produced in type 1a supernovae, but that wouldn't be as readily available as stars are. So that could be a possibility, but not necessarily a very stable system.
If I may add something, if we assume that planets have been formed in such a universe and they revolve around black holes, the thing is that the gravity of a black hole is so strong, even a small perturbations could eventually lead to the planet to fall into the black hole. So maybe the development of a complex observers would not be that good in that universe. I mean, if you understand what I'm saying.
Yeah, that would be possible. Yeah.
Uh, if I may add something, if we assume that planets have been formed in such a universe and they revolve around black holes, the thing is that the gravity of a black hole is so strong, even a small perturbations could eventually lead to the planet to fall into the black hole. So maybe the development of a complex observers would not be that good in that universe. I mean, if you understand what I'm saying.
Weil
Because
es
if,
makes sense, das Argument.
yeah,